Okay, thank you very much for the invitation. Unfortunately, I can't come to Edinburgh in person, but I would like to thank the organizers for allowing me to give an online talk. And today I will talk about a virtual analog of BFN's construction of Coulomb branch and its connection with enumerative geometry, and especially quantum K-theory. Okay, so let me start. So first, let me review the BFN's construction of Coulomb branch. So let's take a reductive group G, and for simplicity, we assume its pi1 is torsion-free, and we have a G representation N. BFN's construction starts with F1 Grassmannian, which is the moduli space of principal G bundles on the formal disk and trivialization on the puncture disk. And the central objects of BFN's construction are these two moduli spaces of triples, and one is called T and one is called R. And the space T consists of so a point in the space T consists of a point in the F1 Grassmannian together with a section of the associated vector bundle. The vector bundle associated with this representation and the principal G bundle. And in particular, it has a presentation like this, so you can write it as a pair G and S. So G is an element in the group GK, and S is a section in this N double bracket Z. And in particular, the space T is a vector bundle of infinite rank over F1 Grassmannian, so it's a smooth over F1 Grassmannian. The other moduli space of triple R is a closed subspace in this T. So in the space R, we require that the section satisfy another closed condition, which says that the restriction of the section to the puncture disk, if you send it by the trivialization, then it extends over the former disk. And in this presentation, so this condition is like this. So the product of G and S also lies in this lies as a regular section of this bundle. And the space R is no longer smooth over the F1 Grassmannian. And in this, in BFN's construction, this is the analog of the Steinberg correspondence as in the Springer resolution. And all of these spaces, they admit a GO action from the left. And in this great work of Braverman, Finkelberg, and Nakajima, they considered the GO equivariant Bremmer homology of this space R. And the central result in their paper is that they proved there is a convolution product which is commutative on this homology group. And then they define the Coulomb branch to be the spectrum of this convolution algebra. And they also proved some properties of this Coulomb branch. For example, it's normal and irreducible, and it serves as the correct objects, which is predicted by physicists. And what is amazing about this BFN's construction is that it comes with a natural quantization. So if you consider the GO times C star Q equivalent homology, where the C star Q here is the one-dimensional torus which scales the formal disk. This Q is an equivalent parameter which I will use later. So I will group C star Q. And if you consider this extra C star action, then this convolution algebra is no longer commutative, and it's a natural quantization of this commutative convolution algebra. And there is a Poisson structure on this Coulomb branch coming from this quantization. And in BFN's work, they also showed that there is a K-theoretic version, and you can add flavor symmetry to this construction. So if there is a torus, an extra torus action T on N, which commutes with the gauge group G, then you can add this T to the group to this equivariant homology or K-theory. And in this talk, I will concentrate on the K-theoretic version and on the quantized version. And the Coulomb branch comes with a natural grading. It's graded by the connected components of the Efron-Grassmannian, or equivalently the pi1 of the gauge group G. So it's like this. And in this zeroth piece, there is a Cartan subalgebra, which given so it's given by the coefficient ring of this equivariant homology or K theory. So this Cartan subalgebra contains the equivariant parameter with respect to the gauge group, the C star Q, and the flavor group. So I will denote these equivariant parameters by S to chi. So this is S is the coordinate on the maximal torus of G, and this chi is a character of G. And Q is the equivariant parameter of C star Q, and these A's are equivariant parameters of T. Okay. So this is the general story. And in the special case where the gauge group is abelian, so it's a torus C star to the K, the BFN's Coulomb branch has a very explicit presentation. In the following, when this gauge group is abelian, I would denote this group by K, by capital K. And in this case, the representation can be decomposed into one-dimensional subrepresentations, and each one is given by a character of the gauge group, which is a vector in this rank K lattice. And the flavor group now is C star to the N. And for each one-dimensional subrepresentation, we associate the equivariant parameter AI, which corresponds to the standard character of this flavor group T. And in this case, the Efron-Grassmannian, if we are only interested in this reduced structure, then it can be identified with this rank R lattice, and we can also identify it with the pi1 of the gauge group or co-characters of the gauge group. And the space, the modular space of triples T and R admits very explicit presentation like these. And in this case, what's special about the space R is that it's also smooth over the Efron-Grassmannian, just like T. And this is not true for non-abelian case. So over each point, Z to D, this space R is just a infinite dimensional vector space. So you can see that its K theory is generated by these structure sheaves of these of the fibers of R over these points in the Efron-Grassmannian. So these would be the generators together with the equivariant parameters coming from this group. So so as a group A, this Coulomb branch A is generated by these generators R sub D over these equivariant parameters. And the relations can be written down explicitly like this. It's these relations are essentially determined by computing the K-theoretic Euler class of something like this. So this is a virtual bundle which comes from the intersection of these components of this R. So I will not go into the details, but yeah, this is essentially the computation. And here in this relation, the right-hand side consists of a bunch of Pohama symbols. So these are just the products, like some products like this. And here I would like to emphasize that this Polynomial symbols, these polynomial symbols also make sense when these numbers are negative. So when these numbers are negative, we just define these polynomial symbols by maybe this a little bit by this quotient of two infinite polynomial symbols. And one from this explicit presentation and actually from definition, one can see the properties that the abelian Coulomb branch satisfies. So one relation or properties of these generators that if you commute this R sub D and add to the chi, then a power of Q comes up. So and this exponents is a pairing between this character and co-character. And R sub 0 is just identity. And a crucial property satisfied by these generators that for two co-characters C and D, if they're pairing with all the characters from the representation have the same sign, then R sub D times R sub C times R sub D is equal to R sub C plus D. And in particular, they're commutative. And by this property and also by this property, actually the relations here actually reduce to the relations here. So we only need to compute the product between R sub D and R sub negative D. So it becomes something like this. And the grading is the Coulomb branch is graded by this just this round K lattice. And yeah, okay. So this is a brief review of B-events construction. So the problem I'm interested in is the connection between this Coulomb branch and innovative geometry, especially the innovative geometry of quasimaps. And so this idea comes from these two. So this current slide and the next slide, which are two previous works, which are quite inspiring. So this is a physicist's work. It's called Vortices and Vermos. So it says that homological quantized Coulomb branch, which physics called monopole operators, they can act on the moduli space of quasimaps, which is this moduli space of vortex moduli space in physics language. The homology of the quasimap, the moduli of quasimaps, and the targets of this quasimaps is the GIT quotient of n by the gauge group G. So it's the pay attention. It's a GIT quotient. It's not the hyperkähler quotient. So this space is not does not have a symplectic structure. And the result of this construction is that one can realize a Verma module of this quantized Coulomb branch. And moreover, the generating function of the quasimaps, which is the innovative invariance we're interested in innovative geometry, this generating function can be expressed as some kind of characters of this Verma module. And also, the quantum differential equation has some interpretation in this way. So in this sense, this quantized Coulomb branch is closely related to innovative geometry. And another reason why this is interesting is that from this innovative geometry, we can try to construct some representations of this quantized Coulomb branch. And I should mention there is some other group of works which related to this BF and Springer theory. So from the Springer resolution point of view, it's natural to consider this GIT quotient instead of the hyperkähler quotient, because the representations of this so the algebra comes from the Springer resolution itself, but the representation comes from Springer fiber, and the Springer fiber they they don't necessarily have this symplectic structure. So, yeah. So this is the first motivation. And the second motivation comes from this earlier work of Sasha Braverman. So in this work, Braverman shows that there is a G action, which is a Lie algebra, G action on the intersection homology of moduli space of Schwerenfeld's cross map into G mod B. And by this construction, he can also construct a Verma module of this G. And the J function, which is the innovative invariance of G mod B, can also be expressed in terms of this is a Verma module. So it can be expressed as some kind of Whittaker function. And moreover, Braverman used this Whittaker function construction to prove that the J function of G mod B satisfy the quantum total system. So this is quite surprising and quite surprising result in innovative geometry. So it's great that from this geometric exploitation theory, one can obtain some innovative geometry results. And yeah, there is also a K-theoretic version. So yeah. So now let's look at this simple. Yeah. So now let's look at a simple example, and let's see how this quantized Coulomb branch can act on the homology moduli space of quasi maps. So the example is like this. So the gauge group C star and the representation Cn, and action is given by this. So all the weights are 1. And the GIT quotients P n minus 1. And these are the relations of the Coulomb branch. So it's generated by R sub 1 and R sub negative 1 as plus minus and all these other equivalent parameters. And this crucial relation between this R1 and R negative 1 is like this. So the right-hand side is a product of 1 minus AI inverse S inverse. And R sub D is R sub 1 to the D. And for this, you can just use these two relations to compute like this. So this Bahama symbol will show up. And so for this Coulomb branch, so as we mentioned before, this S plus minus 1, they belong to the Cartan subalgebra. So it's in the zeros grading. It's in this zeros grading of the Coulomb branch. And so for this R plus minus 1, we should view them as the nilpotent part of this Coulomb branch. So we need to choose some positive part and negative part, and a natural choice of this positive and negative part is to choose it according to the stability condition theta. So here a natural choice that for theta greater than 0, we choose our negative 1 as the annihilating operator and our 1 as the creation operator. So we define this type of highest weight vector. So this S, which is the Cartan subalgebra, acts by a scalar. So this capital S, for now, you can just view it as a formal variable, or it's just a scalar. And we claim that our negative 1 acts by 0. So after this definition, you can an immediate result is that you can multiply this R negative 1 V by R1 from on the left hand side. You get R1 R negative 1 V is 0. But by this relation, R1 R negative 1 is this product of this polynomial of Laurent polynomial of S. So you immediately get that this capital S has to satisfy this equation. So so once you have this highest weight vector, then the eigenvalue of this S has to be a solution of this equation. And you may have noticed that this equation is actually the relation in the K-theory of P n minus 1. So in this way, this capital S can actually be identified with the tautological line bundle in P n minus 1, which is the K-theory class. So so this is the highest weight vector. So there's eigenvalue. So so this Cartan subalgebra acts actually through this Coulomb surjection. So Cartan subalgebra is this polynomial ring in this characters. But now if we define the highest weight vector and apply this Cartan subalgebra to the highest weight vector, then the eigenvalues has to lie in this Coulomb surjection of the Cartan subalgebra. So here's the Verma module. So we apply the R sub D, where D is positive, to the highest weight vector and generate this module. So this becomes a Verma module. And you see that for each D, you have one piece of this Verma module, which can be identified with the K theory. So for each D, the degree D piece of this Verma module is supposed to be identified with the quasi-maps of degree D. And actually, this construction of Verma module can also be realized in the geometry of BFN's construction. So this is a convolution diagram used in BFN's construction of Coulomb branch. So the convolution product of Coulomb branch is obtained by this top row. So it's from these two products of R, you pull back and push forward to this R, you get the convolution products. But also, if you look at this bottom row, then you actually get an action of the Coulomb branch on this K theory of the space T. It's a right action. And you can also look at this T and take the structure shape of this T over the points of the Arfan-Grassmannian, and you can also compute explicitly the action of these generators R sub D on these generators of the K theory of T, and you write it explicitly, and you can see that this action is exactly the same as the action of this Verma module, actually. And after this localization by this C star Q, the fixed locus of the space T can actually be identified with the degree D quasi-maps. And also you have to apply this Coulomb surjection. Yeah. So this is a very vague description of this construction of this Verma module from this space T, which is acted on by the Coulomb branch from the right-hand side. And as expected, we can obtain the Whittaker vector and Whittaker function from this Verma module. And from this explicit formula, you can see that this Whittaker function is exactly the K-theoretic I function for Pn minus 1, which is what we expected. And also the quantum Q difference equation, quantum K theory, quantum K theory ring can also be obtained in this way. So this is roughly how we can get innovative geometry, invariance, and other structures from this representation of Coulomb branch. And this is for this example Pn minus 1. But this example is a little bit special. And when you try to consider more general examples, then actually a lot of difficulties show up. And a central difficulty is the third one. So the first one and second one, we'll talk about it later. So the central difficulty is the third one. So we start with this N and the gauge group K. And we study its Coulomb branch, and the Coulomb branch is originally associated with this 3D n equals 4 theory. So it's Coulomb branch of the 3D equals 4 theory. So for such examples, usually we'll see that it's if you look at T star n, and if you apply the hypercube quotient, then you get some interesting spaces. So these 3D n equals 4 Higgs branch and 3D n equals 4 Coulomb branch, they are interesting objects. And if you only take this vector space n and then apply this GIT quotient, you usually don't get very interesting objects. So these GIT quotients themselves may be just trivial. So for example, for this example, so n is C3 and k is C star square, and the charge matrix is like this. Its Coulomb branch is it's the mirror. So this is a mirror theory to T star P2. So it's actually very interesting if you consider it's a hypercube quotient like this. But if you just consider the GIT quotient, you just get C. Well, if you just choose any generic stability condition, the GIT quotient will just be C. So there's not too much interesting geometry in this GIT quotient. And another example is Pn minus 1, but for the negative stability condition. So usually when we consider this Verma module, for example, in the representation of semi-simple Lie algebras, for any wild chamber, you can construct a Verma module. So you also expect the same in this case. So here we choose theta greater than 0, and we choose R negative 1. Well, here we claim R negative 1V is 0. You also expect that if you choose theta less than 0, here you should put R1V equal to 0, and you can also construct a Verma module in the opposite direction. However, for this GIT quotient, if you choose theta less than 0, you get an empty GIT quotient. So it's not you don't get something similar to Pn minus 1. So this is why this is the third difficulty here. So the idea my idea here is to consider, instead of this simple GIT quotient, we consider this T star n and its hyperkiller quotient by k. This is the Higgs branch of the 3D n equals 4 Higgs 3D equals 4 theory. And in this way, we will get more interesting examples, and also these ambient spaces, they have very rich innovative geometry, which is studied by Andrei Okhonkov and other people. And hopefully, well, this is maybe a goal in the future. Hopefully, we can understand 3D mirror symmetry using this construction. Yeah, so this is why why we want to consider this hyperkiller quotient. Yeah. So now let me briefly introduce this innovative geometry of these 3D equals 4 Higgs branches. So again, we have this reductive group G, which is a gauge group, and the representation. And we have the flavor symmetry, but now we have one more C star. This is C star H bar, which scales the cotangent fiber of T star n. And we take the T star n quotient by G. This is a hyperkiller quotient. We will always So in this type, we will always assume that this X is smooth with isolated T fixed points. And we'll also assume the covariance surjection, which for hypertoric varieties is automatic, and for quiver varieties is due to this work. And the central objects in the intuitive geometry of such ambient spaces Rx is this descendant vertex function proposed by Andrei Konkov. So it's called it's called VQ. So this is a power series in a scalar parameter Q, where the coefficients are some rational functions in the covariant parameters. This capital Q is what we call scalar parameter. So it's a record. So this parameter records the degrees of the quasimap, and the degrees of the quasimaps, they form a cone in pi1 of the gauge group, and this cone depends on the target space X. So it's the cone of effective curve. Well, usually it's the cone of effective curves, but it's actually a little bit different from that. But you can always you can always have a cone of effective quasimaps. Actually. And these coefficients V sub D, they come from the K-theoretic counting of quasimaps from P1 to X. And A here is a equivariant parameter. It's a collection of equivariant parameters of T, and Q is the equivariant parameter of C star Q. Here the C star Q is a C star on P1, and Q is a tangent space, tangent character P1 at 0. I use the same notation C star Q as before. So C star Q in Coulomb branch scales a formal disk, and here is the scales of P1. So these two C star Q, they're essentially the same. Okay, and here there's another object called tau S. So this is a insertion called descendant insertion one can put in this quasimap. So this is a class in the K theory of the K theory before the covariance surjection. So it's a Laurent polynomial in terms of characters of G and other equivalent parameters. So in other words, this tau S is an element in the Cartan subalgebra of the Coulomb branch. Yeah. So yeah, in this space. Okay. And here you also have to do some localization. So you have to localize these coefficients a little bit, because they're the modular space of quasimaps. So the evaluation map from the modular space to X is not proper, and only if you apply C-star localization, it becomes proper, and you have to localize some coefficients. So these vertex functions, they contain the information of the geometry of these quasimaps, and a crucial property satisfied by these vertex functions is that if you scale these vertex functions by some exponential factor, then they satisfy Q difference equations. So this is the Q difference equation stated for these descendant vertex functions. So if you shift this scalar parameter capital Q by a Q difference operator, then you get another descendant vertex function. But this descendant is multiplied by this as the chi, and this chi comes from the chi here. And this quantum difference equation, or quantum Q difference module, contains the innovative geometry of this target space X. And you can also get other innovative geometric objects from this quantum Q difference module. So if you let this little q goes to 1, you can recover the Betti algebra or the quantum K-theory ring from this Q difference equations. And yeah, so this is related to the 3-point functions of these quasi maps, and also this quantum K-theory ring is also called Betti algebra because the relations in this quantum K-theory ring can often be identified with Betti equations. Okay, so let's get back to the example Pn-1. So in the example Pn-1 here, so we can consider its analog in this 3D X4 theory. So we consider T star n quotient by this C star. So now we get T star Pn-1. And so well, I should mention here. So apart from the third difficulty, we also have other 2 difficulties. So we have this second difficulty. So the second difficulty says that if there are some negative ways. So if by negative ways, I mean you for some co-character D here in the effective cone of X, in the effective cone X, you may get so this pairing chi with chi I with this co-character D may be negative. So if that happens, then your cross maps may have obstructions, and your modular space of cross maps may not be smooth. And in this geometric construction, of this module, you have to deal with this obstructions of this modular space cross maps. So here, what happens is that if you consider this hyperkähler quotient, then you always get obstructions. So for example, this is a comparison of Pn-1 with T star Pn-1. So in the Pn-1 case, all class maps have degree positive degrees. So they have deformations. So deformations come from H0 of O D, but obstructions are 0 because H1 of O of D would be 0 when D is positive. But for T star Pn-1, you have another half coming from the cotangent direction. So you have H0 O negative D, and you also have H1 O negative D. So this part in the obstruction will not vanish. So you always have a non-trivial obstruction theory in T star Pn-1. And that's why in this vertex function for T star Pn-1, you have this contribution in the numerator. This H bar ARS. So this part comes from the obstruction. And the observation here is that the modular space of class maps for Pn-1 and for T star Pn-1, they are essentially the same, at least for positive degrees. But the obstruction theories are different. So in this hyperkähler case, we have non-trivial obstructions here. So this is what we can learn from this innovative geometry part. So the idea here is that well, yeah, as in this second second difficulty. quasi maps may have abstractions. So the idea here is that because quasi maps have abstractions, so in this action of branch on the modular space of quasi maps, we may have to also introduce abstraction theory in this Coulomb branch. And as we can learn from this observation, we want to use the same modular space and put some non-trivial abstraction theory. So the idea is that we use the same modular triple R, but we introduce some non-trivial abstraction theory. This is again the convolution diagram in BFN's construction. If we look a little bit more in details, we can extend this diagram to the third row, and we factor this map P into P prime and delta. So other maps, so this Q is a smooth projection, this P prime is a smooth projection, M is a proper map which we use to do the push forward, and this delta is a diagonal embedding, which is it's an embedding of this NO into this double product of NO. And because NO itself is smooth, so this delta is a regular embedding. So all the convolution products is given by pullback and push forward along this way. So you actually all the intersection theoretic operations involved in this construction are smooth pullbacks and Geisen pullback along this regular embedding and purple push forward. So the idea is that we need to put some non-trivial abstraction theory. So this third row here, all spaces in this third row, they are smooth over alpha Grassmannian times alpha Grassmannian. So in particular, their cotangent complex, the cotangent complex adjusts the cotangent mondo. And we replace this cotangent complex by a symmetric abstraction thing like this. So we add an abstraction part, and we associate this abstraction part by a non-trivial equivalent parameter. And then in this third row, we replace all the smooth pullback by a virtual pullback, and the virtual pullback comes from these abstraction theories. And we also replace this Geisen pullback along this regular embedding by something called a virtual Geisen pullback. And in this step, you also need to localize some of the coefficients, and this is why we need this non-trivial equivalent parameter here. And in this way, we can generalize BFN's construction of this convolution products to a virtual convolution product. And now you can consider this equivalent K-theory of this space R together with this virtual convolution product. And for this ring, we call it the virtual Coulomb branch. Yeah, so this is the geometric construction. And as in BFN's usual Coulomb branch, we have some explicit presentation of this virtual Coulomb branch. So you can see, so the virtual Coulomb branch is also generated by R sub D, and well, it's also generated by R sub D and these and other equivalent parameters. And the difference is that we now have an extra parameter H bar. And also this R sub D is no longer the structure sheaf of R over these points, but it's the virtual structure sheaf. And most of the properties are the same. Also, we have this property if C and D have the same sign for all the characters, then they commute. They commute. And now by this by this abstraction theory we introduce, in this relation of the virtual Coulomb branch, we see that these denominators show up. Well, they are, well, essentially if you just take the numerator and invert this AI inverse, you invert it to AI, and for this S negative chi, you invert it to S chi. And for the Q's in this Polynomial symbol, you invert them to Q inverse, and you get this denominator. And you also put this non-trivial equivalent parameter H bar, then you get this relation. And you see here this relation, this right-hand side lies in the localized version of the K theory. It's not in the original K theory. And okay, so this is the relations for the abelian virtual Coulomb branch. And in this T star Pn minus 1 example, so these are the relations. And here, this is what I mentioned briefly before. So when this D is negative, this Polynomial symbols also make sense, but this Polynomial symbol for a negative number, it's actually it's something in the numerator. It's something in the denominator. It's not in the numerator. So this is also like the other. It's also something in the denominator. And you can also define the Verma module in this way, and you get the Verma module. So yeah, this is what happens for T star Pn minus 1. And this is also the geometric story. The same story actually applies to the, you can consider this space T and consider this geometric construction of the Verma module. And also this vertex function can be obtained as the Whittaker function of this virtual Coulomb branch. And now, as before, we ask for more general cases. So in this case of virtual Coulomb branch, more general cases are hypertoric varieties. So they are general hypercolored quotients of abelian groups. So here comes the other difficulty. So recall that we have 3 difficulties. This one and this abstractions, and we have another difficulty. That's this first difficulty says that for different fixed points of this target space, we may have different effective cones. So what does it mean? So what's special for the example Pn minus 1 and the example T star Pn minus 1 is that we have a canonical choice of the space N, which is a half in the symplectic representation T star N, which we can call a polarization. So for Pn minus 1, this representation has all weights, so all the weights of N are positive. And for T star Pn minus 1, there is this canonical polarization N, whose weights are all positive. And this is not true in general. For example, for this example, if you look at this charge matrix, so these characters, so each column is a character. So these 3 characters add up to 0. So there's no way to choose a polarization in T star of C3 such that that polarization contains characters which are positive with respect to all the effective curves of Higgs branch. And so you can also look at the fixed points of these hypertoric varieties. So the difficulty I just mentioned, if you look at the fixed points, that difficulty showed up as as the following. So for different fixed points, you have different effective cones. So for each fixed points, you have a cone of effective curves mapping into that fixed points. And for different fixed points, so in the T star PM -1 example, for every fixed points, you always have the same effective cone. So because you only have a rank 1 lattice of curves, and the cone is always the positive cone. But for other Habitaric varieties, for example, this one, so the Higgs bunch, the Habitaric variety will be the A2 resolution. There will be three effective cone, and three fixed points, and the effective cones of these three fixed points will all be different. And the effective cone of the Higgs bunch itself would be the union of all the union of effective cones of all the fixed points. So and this to solve this problem, the idea is that for different fixed points, we need to choose different polarizations, and that means for different fixed points, we choose an n. We choose a different n in the starting data of the Coulomb, of the definition of the Coulomb branch. So yeah, so the result of this idea is that we have some modification of these generators. So previously we have this virtual structure sheaf of R, which we call R sub D. And now we choose different polarizations for different fixed points, which for this I call it the mixed polarization. And the generators, I call them curly R sub D. And they satisfy much better properties than the generators before. So this property is the same, and however, so previously only for those C and D which have the same sign for all the characters, we have this identity. So R sub D, R sub C, and R sub D commute. But now, for all C and D's in the effective cone of X, or in the negative effective cone of X, we have this identity. So that means if we take curly sub D for all D in the effective X, then we have, so these form a commutative subalgebra, and you can so they form a natural choice of positive or negative part of your Coulomb branch, which you can take to construct the Verma module. And in this case, well, the relations can be written like this, and you have to invert. You also have to invert some coefficients according to the signs of these DIs, and also an observation is that the ways of inverting these coefficients, they exactly coincide with the relations in the presentation of the K-theory ring of Habitaric varieties. So what I mean by that is that the K-theory of Habitaric varieties has a bunch of relations. So it's you can write it as a product according to. So these relations are parameterized by the effective curves of X, and according to these signs of this DI, you put 1 minus AIS or 1 minus H bar AIS, and these coefficients, these polynomials here you invert in this virtual Coulomb branch with mixed polarization. They're exactly those which do not appear in this relation. So for DI positive, in this relation you have 1 minus AS, but for D positive in this denominators appearing in this Coulomb branch, you have 1 minus h bar ARS. So so in this way, in this sense, this Coulomb branch can be defined over the localization of this ambient ring, well, this Cartan subalgebra, with respect to the ideal appearing in this covariance structure. So yeah, so what I want to say here is that this definition of this mixed polarization is compatible with this presentation of the K-theory ring of hypertonic varieties. Okay, so the result is using this virtual Coulomb branch with mixed polarization, we can define the Verma module and the Whittaker function. And you can geometrically, you can realize the action of this virtual Coulomb branch on the K-theory of quasimaps into these fixed points. And you can realize the vertex function as the Whittaker function. And also you can describe the quantum Q difference equations in terms of this, well, so this equation is the same as before. And now we have another equation coming, which is described by the virtual Coulomb branch. So this equation says this equation describes the what you get if you apply a Q difference operator to the vertex function, and this one describes what you get if you multiply the vertex function by any parameter. So what you get also a vertex function, but this descendant insertion is multiplied by this generators R sub D and R sub negative D on the left hand side and right hand side. And using this description, at least in the abelian case, we can recover all the Q difference equations satisfied by the vertex functions. Okay, my time's running up, so let me skip this part. So the previous story is for abelian case, and in the non-abelian case, the Coulomb branch and the Verma module, they are somehow complicated. But for the vertex function, we have some abelianization results. So the vertex function can be expressed in terms of the abelian quotients of this general hyperkähler quotient, and we also have a description of the quantum Q difference module in terms of this virtual Coulomb branch of the abelianized of this abelian quotient. So this Coulomb branch is essentially about this abelian quotient. It's not about X itself. So this is somehow an abstract description of this Q difference equation. It's not so yeah. So these relations are still stated in terms of these generators of the virtual Coulomb branch. It's not so explicit as one hoped. So this is a application one can get from this result. So if you vary the stability condition of this GID quotient, you can see that this virtual Coulomb branch, this generators of the virtual Coulomb branch behaves very well. So if you vary theta, then these generators for another choice of theta, they are somehow just some kind of inverse of the original generators. And then you play with these relations in the quantum Q difference module, then one can prove that the quantum Q difference module is invariant under this variation of GIT. Okay, so let me, yeah, this is some future work one can develop along this way. So maybe let me stop here. Thank you very much.